Howdy. This video is on Van der Waals equation, Maxwell's equation, and Graham's law. Van der Waals equation can be used to calculate parameters for non-ideal gases, for when gases are no longer behaving ideally. Maxwell's equation relates average speed, temperature, and molar mass. Graham's law can be used to calculate the relative rates of effusion and diffusion of gases. After watching this video, you should be able to describe how Van der Waals equation is related to the ideal gas law and related assumptions. You should be able to use Van der Waals equation to calculate different macroscopic parameters for gases. You should be able to describe the relationship between kinetic energy and average speed. And you should be able to calculate relative rates of effusion and diffusion of gases using Graham's law. And so the ideal gas law, PV equals nRT, works well under normal conditions. The approximations for the ideal gas law is intermolecular forces are negligible and volume of gas particles are negligible. Good approximation under normal conditions. But as you lower the temperature, all gases do eventually condense. And so as you lower the temperature, intermolecular forces no longer become negligible. If you get to high pressure, then the volume of the gas particles themselves is no longer negligible. We also used the ideal gas law to derive an equation for the density of a gas, and we found the density of a gas is equal to pressure times molar mass divided by the gas constant and temperature. And we also used the ideal gas law to derive Dalton's law of partial pressures, which just says that the total pressure is equal to a sum of the partial pressures. And so if we start with PV equals nRT, and we divide both sides by nRT, we would get that PV over nRT should be equal to 1. And so the dashed line here corresponds to an ideal gas. It corresponds to PV over nRT equal to 1. And you can see that the deviation is deviation from ideal behavior. And so hydrogen deviates one way, nitrogen, methane, ethene, and ammonia deviate a different way. And notice that the higher the pressure, the bigger the deviation. And so an interesting question would be, which of the gases behaves least like an ideal gas? And the biggest deviation from that dashed line for these gases would be ammonia. So we'd say it's the least ideal. And why would ammonia be least ideal? Well, probably because it has hydrogen bonding, and so intermolecular forces become important, and also it's fairly large. Hydrogen is pretty small, nitrogen is pretty small, and so they're pretty close to that dashed line, which represents ideal behavior. And so when a gas deviates from ideal behavior, we can use Van der Waals equation. And Van der Waals equation is right here. And the way I think about it is, so in this square bracket here, you can think about P, V equals nRT. And so you have a correction term here for intermolecular forces. N squared times A. A is a parameter that is different for each gas, divided by V squared. So again, the square bracket, think about it in terms of P and this as a correction. And so the idea being that because of intermolecular forces, the gas particles are attracted to themselves more, and so hit the container less. And so the pressure, the measured pressure, is actually smaller than what it should be. And so that's why this correction term is positive. Again, it's a correction term for intermolecular forces. And then here you have V minus NB, and this is a correction term for the volume of the gas particles themselves. And so N, again, is the number of moles. B is a Van der Waals parameter, which is different for each gas. And so the concept here is that because the gas particles themselves take up some of the volume, the measured volume is a little bit too big, because not all that volume is accessible for the gas particles. And so that's why this term is actually negative. And so if we look at an example, say, so chlorine has a value of A of 6.49, B of 0.0562. And so for 8 moles of chlorine in a 4-liter tank at 27 degrees Celsius, we can try to calculate the pressure using ideal gas law, and we get 49.3 atmospheres. We can also calculate using Van der Waals, and we see a very different number of 29.5 atmospheres. Now, 8 moles in 4 liters, remember, At STP, 1 mole takes up 22 liters, and so you imagine the pressure should be quite high, and there should be a deviation from ideal behavior. Now again, the van der Waals constants A and B differ for each gas. And so helium, here's your values, argon, hydrogen, nitrogen. You notice that as you get bigger and stronger intermolecular forces, these get bigger. For ideal behavior, if we go back here, if this was ideal behavior, that would correspond to A being 0 and B being 0. It would correspond to those correction terms being 0. And so the farther away from 0 for A and B, the less ideal the gas is. So all gases have the same average kinetic energy at the same temperature. At higher temperatures, kinetic energy is larger.
Gas molecules are in constant motion and frequently collide with one another. Although not all the molecules in a gas sample move at the same speed, the higher the temperature of the gas, the greater the average speed and kinetic energy of the molecules overall. This higher level of energy allows molecules to disperse more readily, which is one reason we smell aromas better when temperatures are higher.
So the higher the temperature, the higher the average speed. Also, the broader the distribution, the average speed. But again, it's important to remember that all gases have the same exact average kinetic energy at the same temperature.
Cars on highways travel at a variety of speeds. To show the distribution of automobile speeds, we could plot the number of cars moving versus their velocities. Molecules in the gas phase show the same variability of speed. Plots of molecular speed distributions are called Boltzmann plots.
And again, this shows us that we have to think about in terms of average speed because there's going to be a distribution of speeds. Now, all gases have exactly the same average kinetic energy at the same temperature, but the speed will differ. It depends on the size of the gas particle. The more massive the gas particle, the slower. The less massive, the faster. But again, the average kinetic energy will be the same. The average kinetic energy depends only on temperature.
At any given temperature, the molecules of a gas are in continual motion. At any instant, some molecules have more kinetic energy of motion than others. With increasing temperature, the average kinetic energy increases in proportion to the absolute temperature. This graph shows the distribution of molecular speeds for a particular gas at two different temperatures. Notice that the most probable molecular speed, given by the peak of the curve, increases as the temperature increases. Here we see a mixture of two gases with different molecular masses, helium and neon. The more massive neon atoms move more slowly, but they possess the same average kinetic energy as the helium atoms. At a given temperature, the distribution of molecular speeds for helium is much more spread toward high speeds than for neon. As the temperature increases, the average speeds of both helium and neon atoms increase. At any given temperature, their average kinetic energies are the same.
This is kind of interesting. The average kinetic energy is the same at the same temperature, no matter what the gas is. And so here we have helium and neon. At the same temperature, their average kinetic energy is identical. Their speed is different because remember, kinetic energy is equal to 1/2 mv squared. So you notice that the helium, because its lighter, is going to have a higher average speed. It's also going to have a broader distribution of those speeds. Here's a plot of oxygen at 25 degrees Celsius, oxygen at 1000 degrees Celsius. Higher temperature corresponds to higher kinetic energy, higher average speed, and a broader distribution of that speed. That's kind of interesting. If we look at gases all at the same temperature, all of their average kinetic energies is the same. But notice as you go to the lighter gas, you go to a higher speed, and you also go to a broader distribution. looks very similar to going to a higher temperature. You go to higher average speed and a broader distribution. But again, please remember, all gases have exactly the same average kinetic energy at the same temperature. Lighter gases will have a higher average speed and a broader distribution. And so kinetic energy is just equal to 1/2 mv squared. And so if you're comparing gases and gas has a bigger m, then the v squared will have to be smaller if their kinetic energy is going to be the same. And so the average kinetic energy depends only on the temperature. And so we can talk about what's referred to as a root mean square speed. So you take the speed, you square it, take the average, and then you take the square root. And Maxwell's equation says that the root mean square speed is equal to the square root of 3RT over m, where r is the gas constant, t is temperature, and capital M is the molar mass. And so what this shows you is that higher temperature corresponds to higher root mean square speed. Bigger molar mass corresponds to slower root mean square speed. And so we saw that kinetic energy is 1/2 mv squared. We saw that the root mean square speed is equal to square root 3RT over m. And so if we plug in this for our v squared, we get kinetic energy is equal to 1/2 m 3RT over m. Because remember, it's v squared, and so we get rid of that square root sign. Now, the molar mass is just going to be Avogadro's number times the mass of a single particle. So the lowercase m we're looking at for a single particle. Molar mass is Avogadro's number times the mass of a single particle. And so the m's cancel, and we get 1/2 3RT over Na, where again Na is Avogadro's number. And so we can just rewrite it as 3RT over 2Na. So the kinetic energy of the gas is equal to 3RT over 2Na. And so it's kind of interesting. What that shows you is that the kinetic energy depends only on temperature. Now we calculated the kinetic energy for a single particle, and then if we want to do it per mole, we'd multiply by Avogadro's number. And so for a single particle, we have, this is the average kinetic energy, and it depends linear on temperature. Multiplying by Avogadro's number, we get the average kinetic energy for a mole of gas particles, and it also depends linearly on temperature. And so gas can diffuse and effuse. Diffuse is where it's in a room and it just bounces through, goes from one part of the room to another room. Effuse is when you have a small hole in a barrier, and the gas goes from being with a lot of gases into vacuum, and so you have effusion. And so diffusion, the rate of diffusion, rate of effusion depends on the root mean square speed, which depends on temperature and the molar mass. And so what you should expect is that the more massive the gas particles, the slower the diffusion and the slower the effusion.
A stopwatch is started at the same moment as a few drops of liquid bromine are placed in the bottom of a test tube containing air at atmospheric pressure. The bromine rapidly evaporates at room temperature. The reddish-brown bromine molecules diffuse up the tube. Although the bromine molecules are moving at speeds of several hundred meters per second, their constant collision with nitrogen and oxygen molecules of the air cause them to constantly change direction, so that their overall movement up the tube is rather slow. Thus, after 2 minutes, they are only about halfway up the test tube. It actually takes over 3 minutes for the bromine molecules to diffuse up to the clamp near the top of the test tube.
And so it's really kind of interesting. The particles are moving really, really fast, but they keep on colliding with each other, changing direction, and so the diffusion is actually relatively slow, especially for the bromine, which is pretty massive. So the rate of diffusion and effusion is proportional to the root mean square speed. And we saw that the root mean square speed is equal to the square root of 3RT over m, where R is gas constant, T is temperature in Kelvin, and m is the molar mass. And so what this shows us is that the rate of diffusion and effusion is proportional to the square root of 1 over the molar mass. We can just write it like that. Now, if we want to compare the rates of two gases, so we can actually take this equation and then divide it by another equation for another gas, and we get the rate of diffusion of A divided by the rate of diffusion of B is equal to the square root molar mass B divided by the square root molar mass A. So notice that here the rate of A is on top, the molar mass of A is on bottom, the rate of diffusion for B is on bottom, the molar mass of B is on top, and that's again because the rate of effusion and diffusion is inversely proportional to the square root of the molar mass. That's what we see here. And so the ratio of these rates is actually equal to the square root of their ratio of their inverse of their molar masses. And that's actually referred to as Graham's law. And again, you can use it for diffusion and effusion. And so a question we could ask is, which diffuses faster, ammonia or HCl, and by how much? And so ammonia, you're going to have a molar mass of 17. Remember, if the rate of ammonia is on top, the molar mass of ammonia goes on bottom. For HCl, the molar mass is 36. So if the rate of HCl is on bottom, the molar mass of HCl goes on top. 36 divided by 17, and then take the square root, and that gives you 1.5. And so the ammonia should diffuse 1.5 times as fast as the HCl. This is kind of cool. So here we have some HCl here and some ammonia there. And when they hit each other, they'll react to form ammonia chloride, and you'll see a white cloud.
On the right is HCl gas, and on the left is NH3 gas. Where the two meet, a reaction occurs producing ammonium chloride gas. The reaction occurs primarily on the right because NH3 is lighter and diffuses faster.
And so the ammonia is on the left. It goes a farther distance before it hits the HCl, and so the ammonia must have diffused faster. The lighter the gas, the faster the gas. And again, they were at the same temperature, and so they had exactly the same average kinetic energy, but because kinetic energy is equal to 1/2 mv squared, the lighter the gas, the faster the gas. But it's kind of interesting. In World War II, the first bomb-grade uranium-235 was actually produced by gas diffusion. And so uranium-235 is the only naturally occurring fissionable material, but it's less than 1% naturally abundant of all the uranium isotopes. And so you need like 90% uranium-235 to make a bomb, but in nature there's only like 1%. And so you have to separate the uranium-235 from the other isotopes of uranium. And because they weigh differently, what you do is you form uranium hexafluoride into a gas, which is a gas, and then you separate out the different gas particles based on how fast they diffuse. And that's how the first bomb-grade uranium was actually produced. And so Van der Waals equation can be used for non-ideal gases. You should be able to recognize how it's related to the ideal gas law. Maxwell's equation relates average speed, temperature, and molar mass. All gases have the same average kinetic energy at the same temperature, but lighter gas particles are faster. Graham's law can be used to calculate the relative rates of effusion and diffusion. The rates of effusion and diffusion are inversely proportional to the square root of their molar mass. I hope that was helpful.